Hello and welcome. Tonight, we shall embark upon a tranquil voyage through our very own solar system. Come aboard our Ship of Serenity and make yourself comfortable as you are gently carried on a journey of relaxation and discovery. Let's get underway. The solar system is a vast and intricate system of celestial bodies bound together by gravity, centered around the Sun. It contains 8 major planets, dozens of moons, countless asteroids and comets, and many other objects that continue to shape our understanding of the universe. Our journey begins at the center, with the star that anchors it all. Chapter 1: The Sun. At the very heart of our solar system lies the Sun, a colossal sphere of incandescent gas that exerts an almost unimaginable influence on the space around it. This star, a near-perfect sphere of hot plasma, is the reason the solar system exists in its current form. It provides the heat and light necessary for life on Earth, and it serves as the gravitational anchor for everything that orbits around it. The Sun is classified as a G-type main sequence star, or G-dwarf, and it is about 4.6 billion years old. Born from the gravitational collapse of a region within a large molecular cloud, the Sun ignited when the pressure and temperature at its core became high enough to sustain nuclear fusion. This fusion process converts hydrogen into helium and releases an enormous amount of energy in the form of light and heat. Every second, the Sun converts about 600 million tons of hydrogen into helium, releasing energy equivalent to the explosion of billions of nuclear bombs. To imagine the Sun, picture a sphere more than 100 times the diameter of Earth, roughly 1.39 million kilometers across. Its surface, known as the photosphere, radiates a brilliant, golden white light. The photosphere appears mottled and grainy, a texture caused by convection currents of plasma rising and falling in vast cells, each several hundred kilometers wide. Above the photosphere lies the chromosphere, a thin layer that glows a reddish hue due to the presence of hydrogen. And beyond that, the corona extends millions of kilometers into space, a tenuous halo of superheated plasma visible during total solar eclipses. Despite being less dense than the layers below, the corona is far hotter, reaching temperatures of over 1,000,000 degrees Celsius. Scientists believe magnetic fields play a key role in this unusual heating. The Sun rotates on its axis approximately once every 27 days, but this rotation isn't uniform. At the equator, the Sun completes a rotation in about 24 days, while near the poles, it takes closer to 35 days. This differential rotation contributes to the twisting and tangling of the Sun's magnetic field, giving rise to sunspots, solar flares, and coronal mass ejections. Sunspots are dark, cooler areas on the Sun's surface where magnetic fields are particularly strong. These can be larger than Earth and may persist for days or even weeks. Solar flares, on the other hand, are sudden and intense bursts of radiation caused by the release of magnetic energy. Coronal mass ejections are even more dramatic, involving the release of massive amounts of solar plasma and magnetic field into space. These phenomena can affect satellites, power grids, and communication systems on Earth when they interact with our planet's magnetosphere. The Sun also emits a continuous stream of charged particles known as the solar wind. This wind flows outward through the solar system, forming the heliosphere, a vast bubble of solar material that envelopes all the planets and acts as a shield against interstellar radiation. The solar wind varies in intensity and speed, shaping the tails of comets and contributing to the beautiful auroras observed near Earth's polar regions. From a visual perspective, imagine the Sun as an ever-roiling ball of fire, its surface a turbulent sea of bright and dark patches. Large arcs of plasma known as prominences can be seen arching above the surface, tethered by magnetic forces. The corona shimmers like a silver veil during an eclipse, and the entire structure pulses with the quiet but constant hum of fusion at its core. The scale and power of the Sun are difficult to grasp. It accounts for 99.86% of the total mass of the solar system. If the Sun were a hollow sphere, it could contain over 1 million Earths. Its gravitational pull extends billions of kilometers in every direction, keeping the planets, asteroids, and comets in their orbits. Despite its immense size and energy, the Sun is just an average star. There are countless others in our galaxy alone, some much larger, some smaller, some hotter or cooler. But to us, the Sun is unique. It is our star, the central beacon in the sky that governs our days, our seasons, and our very existence. As we continue our journey outward from the Sun, we begin to encounter the planets, each one shaped in part by the Sun's warmth, its light, and its far-reaching influence. The first of these is Mercury, the closest planet to the Sun, and our next destination in this voyage through the solar system. Chapter 2: Mercury. Mercury is the innermost planet of the solar system, orbiting the Sun at an average distance of just under 58 million kilometers. It is also the smallest of the 8 recognized planets, with a diameter of about 4,880 kilometers, roughly 1/3 that of Earth. Despite its size and proximity to the Sun, Mercury often remains overlooked, a quiet world of extremes and enduring mystery. To visualize Mercury, imagine a barren, rocky sphere resembling the Moon. Its surface is covered in a dense patchwork of impact craters, ridges, and plains. These features tell a story of billions of years of bombardment by meteoroids and comets, long before Earth had even formed its first oceans. Unlike Earth, Mercury has no atmosphere thick enough to erode or reshape these ancient scars, so they remain preserved in stunning clarity. The largest impact feature is the Caloris Basin, a colossal crater over 1,500 kilometers across, formed by a massive collision early in the planet's history. Surrounding the basin is a concentric ring of mountains, thrown up by the force of the impact, and the terrain within is marked by fractures and lava-filled plains, frozen in time. Mercury's surface also features long, cliff-like ridges called lobate scarps. These escarpments can stretch for hundreds of kilometers and rise as high as a kilometer. They were formed as the planet's interior cooled and contracted, causing the crust to wrinkle and compress. With almost no atmosphere to retain heat, Mercury experiences the most extreme temperature fluctuations in the solar system. During the day, surface temperatures can reach 430 degrees Celsius, hot enough to melt lead. Yet at night, those same regions plummet to minus 180 degrees Celsius, colder than many parts of Pluto. These drastic shifts occur because Mercury rotates very slowly, taking 59 Earth days to complete one rotation on its axis. Mercury's orbit around the Sun is equally remarkable. It completes a full orbit in just 88 Earth days, making its year the shortest of any planet. Its orbit is also highly elliptical, bringing it significantly closer and farther from the Sun during different parts of its journey. This elliptical orbit contributes to Mercury's unique solar day, which lasts about 176 Earth days from one sunrise to the next. Despite its small size, Mercury possesses a surprisingly large iron-rich core that makes up about 85% of the planet's radius. This core generates a magnetic field, though it is only about 1% as strong as Earth's. Still, it is notable because magnetic fields are rare among small planets, indicating a partially molten core still capable of conducting electrical currents. Mercury has no moons and no rings. Its lack of atmosphere means there are no clouds, no weather, and no wind to shape the landscape. The sky, even during the day, would appear pitch black, save for the glaring brightness of the nearby Sun, which appears more than twice as large in the sky as it does from Earth. Observing Mercury from Earth is challenging due to its close proximity to the Sun. It is best seen during twilight, shortly before sunrise or after sunset, when it briefly appears as a bright point near the horizon. Because of this, ancient astronomers often mistook it for two different stars, one visible in the morning and one in the evening. Mercury was visited by NASA's Mariner 10 spacecraft in the 1970s, which flew by the planet 3 times and captured the first detailed images of its surface. Decades later, the MESSENGER mission entered orbit around Mercury in 2011 and provided a comprehensive survey of its geology, magnetic field, and chemical composition. MESSENGER revealed evidence of water ice hidden in permanently shadowed craters near the poles, protected from sunlight and preserved in the vacuum of space. The European Space Agency and the Japan Aerospace Exploration Agency have launched a joint mission, BPI-Colombo, which is currently en route to Mercury and expected to arrive in 2025. This mission will provide even deeper insights into the planet's interior, surface processes, and magnetic environment. Mercury may be small and airless, but it offers a compelling glimpse into the early history of the solar system. Its ancient surface serves as a preserved record of a chaotic past, when collisions and cataclysmic impacts were common. In many ways, it is a time capsule, a quiet, cratered relic orbiting in the intense glare of the Sun, waiting to yield its secrets to those who study it. Next, our journey continues to the second planet from the Sun, a world cloaked in thick clouds, sweltering heat, and volcanic plains, the Venus. Chapter 3: The Venus. Venus is the second planet from the Sun, often described as Earth's sister due to their similar size and mass. Yet, despite these superficial similarities, Venus is a profoundly different world, a planet shrouded in thick clouds, dominated by volcanic landscapes, and enveloped by a scorching atmosphere that makes it the hottest planet in the solar system. Venus is about 12,104 kilometers in diameter, just slightly smaller than Earth. However, its surface conditions are unlike anything found on our home planet. The dense atmosphere is composed of over 96% carbon dioxide, with clouds of sulfuric acid suspended high above the surface. These clouds are so reflective that Venus is the brightest natural object in the night sky after the Moon. To the unaided eye, it appears as a brilliant white beacon, often called the morning star or the evening star. Beneath this thick atmosphere lies a rocky terrain sculpted by extensive volcanic activity. The surface of Venus is relatively young in geological terms, estimated to be between 300 and 500 million years old. Much of it is covered in vast lava plains, shield volcanoes, and large dome-like features known as coronae, formed by upwellings of magma that pushed the crust upward. Radar mapping, primarily by NASA's Magellan spacecraft in the early 1990s, revealed that Venus has more volcanoes than any other planet in the solar system. Over 1,600 major volcanoes have been catalogued, Though many scientists believe volcanic resurfacing events may have occurred globally, covering older features and renewing the surface in massive lava flows. Venus lacks plate tectonics, the process on Earth that recycles crust and forms mountain ranges through the shifting of tectonic plates. Instead, its surface is shaped largely by volcanic and internal forces. Despite the absence of plate tectonics, the planet does feature long, winding canyons, impact craters, and elevated regions such as Ishtar Terra and Aphrodite Terra, highland areas comparable in size to continents. The atmosphere of Venus exerts a pressure about 92 times greater than Earth's at sea level, equivalent to the pressure found nearly a kilometer underwater on Earth. Temperatures on the surface average around 465 degrees Celsius, hot enough to melt lead. This intense heat is the result of a runaway greenhouse effect. Sunlight penetrates the thick clouds and warms the surface, but the heat is trapped by the carbon dioxide-rich atmosphere, leading to extreme unstable surface temperatures. The skies of Venus are a dim yellowish-orange, lit by the perpetual twilight created by the thick cloud cover. If you could stand on the surface, visibility would be poor, and the horizon would appear hazy and distorted. The winds at the surface move slowly, only a few kilometers per hour, but high in the atmosphere, winds can reach speeds of up to 360 kilometers per hour, encircling the planet in just 4 Earth days. Venus rotates very slowly and in the opposite direction to most planets, a phenomenon known as retrograde rotation. One rotation takes about 243 Earth days, while its orbit around the Sun lasts only 225 days. This means that a day on Venus, from one sunrise to the next, lasts longer than a Venusian year. This unusual rotation contributes to the complexity of Venus's climate and makes solar patterns on the planet vastly different from those on Earth. Venus has no moons and no magnetic field. The lack of a magnetic field is attributed to its slow rotation and potentially solidified core, which prevents the kind of dynamo action responsible for Earth's protective magnetosphere. As a result, Venus is more exposed to the solar wind, although its dense atmosphere offers some protection. Throughout history, Venus has played a significant role in human culture and astronomy. Ancient civilizations tracked its motion across the sky with great interest, associating it with deities of love and war. Its predictable phases and appearances contributed to early astronomical theories and calendars. Scientific exploration of Venus has posed great challenges due to its hostile environment. The Soviet Union's Venera program achieved the first successful landings, with Venera 7 transmitting data from the surface in 1970. Later missions, including Venera 13 and 14, provided the first color images of the Venusian landscape, showing flat, rocky plains under a thick orange sky. NASA's Magellan mission, launched in 1989, mapped nearly the entire surface using radar, unveiling the topography hidden beneath the clouds. More recently, the European Space Agency's Venus Express studied the planet's atmosphere and weather patterns from orbit, discovering dynamic phenomena such as polar vortices and variations in atmospheric composition. Future missions to Venus are in development. NASA's Veritas and Da Vinci missions, both scheduled for the 2030s, aim to further explore the planet's geology, chemistry, and history. These missions may help answer enduring questions about whether Venus once had oceans and a more temperate climate, and why it evolved so differently from Earth. Venus is a study in contrasts, a planet that mirrors Earth in size and composition, yet diverges so drastically in every other way. Its searing heat, crushing pressure, and acidic clouds make it one of the most inhospitable places in the solar system. Yet, it remains a focal point of scientific curiosity, not only for what it can tell us about our neighboring worlds, but also for the cautionary tale it offers about the power of atmospheric change. As we leave behind the volcanic plains and cloud-covered skies of Venus, our journey takes us to the only known planet that supports life, our own Earth. Chapter 4: Earth. Earth is the third planet from the Sun and the only one known to harbor life. It is a world defined by dynamic systems, shifting tectonic plates, a protective magnetic field, and an atmosphere that supports a delicate balance of temperature and weather. From space, Earth appears as a brilliant sphere of blue oceans, white clouds, green and brown continents, and polar ice caps, a vibrant, living planet. With a diameter of about 12,742 kilometers, Earth is slightly larger than Venus but remains the fifth largest planet in the solar system. Its surface is approximately 71% water, primarily in the form of vast interconnected oceans. These oceans regulate global climate by storing and distributing heat, and they play a critical role in the carbon cycle, dissolving and storing carbon dioxide from the atmosphere. The land masses, 7 continents and countless islands, are varied in terrain, ranging from flat plains and deserts to towering mountain ranges. Earth's highest point is Mount Everest, which reaches nearly 8,850 meters above sea level, while its lowest exposed point is the shoreline of the Dead Sea, over 430 meters below sea level. Beneath the oceans, the Mariana Trench plunges more than 11,000 meters into the Earth's crust, forming the deepest natural point on the planet. Earth's surface rests on tectonic plates, massive slabs of lithosphere that float atop the semifluid asthenosphere. The movement of these plates shapes the planet's surface over time, causing earthquakes, forming mountain ranges, and creating volcanic activity. This process, known as plate tectonics, is unique in the solar system and plays a crucial role in the long-term stability of Earth's climate. The planet's atmosphere is composed primarily of nitrogen, 78%, and oxygen, 21%, with trace amounts of argon, carbon dioxide, and other gases. This atmosphere serves multiple functions. It shields the surface from harmful solar radiation, regulates temperature, and provides the air necessary for life. It also contains water vapor, which condenses into clouds and precipitates as rain or snow, driving the hydrologic cycle. Earth's weather is driven by the sun's energy. Uneven heating of the surface creates wind patterns and ocean currents, distributing heat across the globe. The atmosphere supports a wide range of climate zones, from equatorial rainforests to polar deserts, each sustaining its own complex ecosystems. The planet's rotation on its axis takes about 24 hours, creating the cycle of day and night. Earth's axis is tilted approximately 23.5 degrees relative to its orbital plane. This tilt, combined with its 365.25-day orbit around the Sun, produces the seasons. As Earth moves through its orbit, different hemispheres receive varying amounts of sunlight, leading to the cyclical changes we observe each year. One of Earth's defining features is its magnetosphere, a vast, invisible magnetic field generated by the movement of molten iron within the outer core. This field extends thousands of kilometers into space and deflects most of the solar wind, protecting the atmosphere from being stripped away. When charged particles from the Sun interact with the magnetosphere, they create auroras, vivid displays of light near the poles, also known as the Northern and Southern Lights. Earth has a single natural satellite, the Moon. Roughly 1/4 the size of Earth, the Moon stabilizes the planet's axial tilt and contributes to tidal patterns through its gravitational pull. Formed likely as a result of a giant impact between Earth and a Mars-sized body, the Moon orbits at an average distance of about 384,400 kilometers. From the Moon's perspective, Earth appears as a vibrant, ever-changing sphere, a blue marble spinning in the darkness of space. Earth and the Moon share a gravitational bond that has slowly synchronized the Moon's rotation and revolution, meaning we always see the same side of the Moon from Earth. Biosignatures, the chemical indicators of life, are abundant on Earth. These include free oxygen in the atmosphere, methane, and a wide range of organic molecules. Earth is teeming with life in almost every environment, from deep-sea hydrothermal vents and frozen polar ice to arid deserts and dense jungles. This biodiversity is supported by the planet's liquid water, moderate temperatures, and stable climate. Human civilization has dramatically shaped the Earth's surface and atmosphere. Cities, roads, dams, and agriculture have transformed natural landscapes. Technological advancements have enabled humans to explore not only every corner of their planet but also the space beyond. However, human activity has also introduced challenges, such as pollution, habitat destruction, and climate change, issues that now define much of Earth's scientific and political discourse. Earth has been the subject of extensive study from space. Satellites monitor weather systems, environmental changes, and geological activity. Space missions, such as those by NASA, ESA, and other agencies, have produced thousands of images and datasets that deepen our understanding of the Earth system. Earth is not only our home, it is also our frame of reference for exploring the universe. Understanding how Earth formed, how it maintains its equilibrium, and how life persists on its surface guides our search for habitable worlds elsewhere. In the quest to find life beyond our planet, Earth serves as both a model and a mystery, a thriving oasis in a vast and silent expanse. As we depart our home planet and look beyond its vibrant clouds and life-filled oceans, our journey takes us to the fourth planet from the Sun's smaller, colder, and tinged with a reddish hue. It has long captivated human imagination, Mars. Chapter 5: Mars. Mars is the fourth planet from the Sun and perhaps the most intriguing after Earth. Known as the Red Planet, Mars has captured human curiosity for centuries. It shines in the night sky with a distinctive reddish hue, a result of iron oxide, rust, coating its surface. While once believed to host alien civilizations, modern science has unveiled a cold, arid world marked by ancient landscapes and tantalizing hints of water and past habitability. With a diameter of about 6,779 kilometers, Mars is roughly half the size of Earth. It has only about 11% of Earth's mass and a surface gravity of 0.38 g, meaning a person who weighs 100 kilograms on Earth would weigh only 38 kilograms on Mars. Despite its smaller size, the Martian surface area is nearly equivalent to all the dry land on Earth, making it a vast and varied world in its own right. Mars is home to some of the most spectacular geological features in the solar system. Towering above all is Olympus Mons, the tallest known volcano and mountain on any planet. Olympus Mons rises about 22 kilometers high, nearly 3 times the height of Mount Everest. It spans over 600 kilometers across, its base wider than the entire state of Arizona. The volcano's sheer size is possible due to Mars' lower gravity and lack of tectonic plate movement, which allowed lava to build up in one location over eons. Another awe-inspiring feature is Valles Marineris, an enormous canyon system stretching more than 4,000 kilometers along the Martian equator, 10 times the length of Earth's Grand Canyon. It plunges as deep as 7 kilometers and reveals layers of ancient rock that may hold clues to the planet's geological and possibly biological history. The surface of Mars is a desolate mix of rocky plains, towering dust dunes, extinct volcanoes, and impact craters. Many areas are covered in a fine layer of red dust, blown across the landscape by winds that shape and shift the terrain. Dust storms can engulf the entire planet, sometimes lasting for weeks and reducing visibility to nearly zero. Mars experiences seasons, polar ice caps, and even weather systems, albeit on a much smaller scale than Earth. The Martian year is about 687 Earth days long, and its axial tilt of 25.2 degrees causes seasonal changes similar to those on Earth. At the poles, carbon dioxide and water freeze to form polar ice caps that grow and shrink with the seasons. Temperatures on Mars vary widely, from around 20 degrees Celsius at the equator during the day to minus 125 degrees Celsius at the poles during winter. The thin atmosphere, composed mostly of carbon dioxide, provides little insulation and no breathable air. Atmospheric pressure on the surface is less than 1% of Earth's, equivalent to being at an altitude of over 30 kilometers on Earth, far above the highest mountain. Mars has two small, irregularly shaped moons, Phobos and Deimos. These potato-shaped bodies are likely captured asteroids from the early solar system. Phobos, the larger of the two, orbits very close to the planet, so close, in fact, that it rises and sets twice each Martian day and is slowly spiraling inward. One day, millions of years from now, it may crash into Mars or break apart into a ring. For centuries, astronomers observed Mars and speculated about its surface. In the 19th century, telescopes revealed surface features that some interpreted as artificial canals. These theories were later disproven, but they fueled a lasting fascination with the idea of Martian life. It wasn't until the arrival of robotic explorers that Mars' true nature was revealed. NASA's Viking missions in the 1970s were the first to successfully land and send back data from the Martian surface. Since then, an array of orbiters, landers, and rovers have studied the planet in detail. Rovers such as Spirit, Opportunity, Curiosity, and Perseverance have examined soil composition, atmospheric conditions, and signs of ancient water. There is substantial evidence that liquid water once flowed on Mars. Dry riverbeds, lakebeds, and deltas point to a time when Mars had a thicker atmosphere and a more temperate climate. Some regions show signs of ancient oceans. Ice remains today beneath the surface and in the polar caps, and seasonal flows of salty brines may still occur under certain conditions. One of the central questions in Mars exploration is whether life ever existed there. While no definitive signs of life have been found, the planet's ancient, watery past and its current geochemistry make it a prime candidate for the search. Samples collected by current and future missions may one day return to Earth, offering unprecedented insight into this question. Mars has become a focus for future human exploration. Agencies like NASA and private organizations like SpaceX have developed plans for crewed missions. Mars presents immense challenges: radiation, psychological isolation, and long travel times, but also enormous scientific and symbolic value. To set foot on Mars would be a profound step for humanity. Visually, Mars is stark and striking. The sky has a salmon-pink hue due to suspended dust particles, and sunsets appear blue in contrast to Earth's reds and oranges. The landscape is a palette of rust, ochre, and brown, dotted with jagged rocks and silent horizons. In every way, Mars embodies a planet caught in transformation. Once more Earth-like, now a frozen desert, it whispers secrets of a time long past while holding promise for future discovery. As we leave behind the windswept plains and rust-colored cliffs of the red planet, we journey farther out, to the realm of the giants. Next lies Jupiter, a massive world of swirling clouds, fierce storms, and a family of moons large enough to rival planets. Chapter 6: Jupiter. Jupiter, the fifth planet from the Sun, is the largest in our solar system, a gas giant so massive that it could fit more than 1,300 Earths within its volume. With a diameter of about 142,984 kilometers, Jupiter reigns as a planetary colossus. It is primarily composed of hydrogen and helium, resembling a failed star, and it exerts a profound influence on the solar system through its immense gravity. From a distance, Jupiter is a mesmerizing sphere of constantly shifting clouds and bold bands of color. These bands, alternating in light and dark hues, are formed by powerful jet streams in the planet's upper atmosphere. The cloud tops are composed of ammonia crystals and other compounds, floating in layers of differing temperatures and altitudes. The most famous feature on Jupiter's surface is the Great Red Spot, a gigantic storm that has raged for at least 350 years. This swirling oval-shaped vortex is larger than Earth itself, with wind speeds exceeding 400 kilometers per hour. It appears as a deep red oval embedded within Jupiter's southern hemisphere and is bordered by turbulent white clouds that twist and curl around its perimeter. Jupiter's atmosphere is a deep and dynamic system. It is divided into layers that become hotter and denser with depth. Beneath the visible clouds lies a thick layer of metallic hydrogen, a phase of hydrogen that exists under extreme pressure and conducts electricity like a metal. This metallic hydrogen generates Jupiter's powerful magnetic field, the strongest of any planet, extending millions of kilometers into space. This magnetic field traps charged particles and creates intense radiation belts, far more severe than Earth's Van Allen belts. These radiation zones would be lethal to unshielded spacecraft and pose a significant hazard to future missions. Jupiter rotates rapidly, completing one full spin in just under 10 hours, the shortest day of any planet. This rapid rotation causes the planet to bulge at the equator and flatten at the poles, giving it an oblate shape. The rotation also drives the jet streams that shape its characteristic banded appearance. One of Jupiter's most remarkable features is its extensive system of moons. As of now, over 90 moons have been confirmed, with more still being discovered. The four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Each of these moons is a world in its own right. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes fueled by tidal forces from Jupiter's gravity. Europa has a smooth, icy surface that covers a subsurface ocean, making it one of the most promising places to search for extraterrestrial life. Ganymede is the largest moon in the solar system, larger than the planet Mercury, and is the only moon known to have its own magnetic field. Callisto is heavily cratered and ancient, its surface preserving the history of the solar system's early impacts. These moons provide a microcosm of planetary diversity and have become key targets in the search for signs of life and the study of planetary formation. Jupiter also has a faint ring system, composed mainly of dust particles ejected by impacts on its small inner moons. Unlike the bright and icy rings of Saturn, Jupiter's rings are dark and tenuous, observable only with the aid of spacecraft or powerful telescopes. Humanity's understanding of Jupiter has advanced through numerous missions. NASA's Pioneer and Voyager spacecraft provided early flybys in the 1970s, revealing the planet's immense size and complexity. The Galileo orbiter studied Jupiter and its moons in detail from 1995 to 2003, uncovering insights into the planet's weather, magnetosphere, and satellite system. Currently, NASA's Juno spacecraft orbits Jupiter in a highly elliptical path, studying its gravity field, magnetic environment, and internal structure. Juno has delivered stunning images and valuable data about the planet's polar cyclones, deep atmospheric flows, and auroral activity. Jupiter's auroras, visible in ultraviolet light, are the most powerful in the solar system. They are created when charged particles from the solar wind and Jupiter's own volcanic moon Io interact with the planet's magnetic field. These auroras encircle Jupiter's magnetic poles and pulse with dazzling energy. Visually, Jupiter is a study in motion. Its swirling clouds shift and churn with each passing hour, storms form and dissipate, and the planet's rapid rotation creates a hypnotic ballet of atmospheric dynamics. Through a telescope, observers can see the bands, the Great Red Spot, and sometimes even the Galilean moons aligned in a straight line. Jupiter is not only a giant in size but also in influence. Its strong gravity helped shape the early solar system, possibly directing the paths of comets and asteroids and protecting the inner planets from excessive bombardment. It acts as both a guardian and a gatekeeper, its massive presence a stabilizing force within the planetary family. As we drift away from the turbulent majesty of Jupiter, our journey carries us further into the realm of gas and ice. The next destination is Saturn, a planet of golden rings, subtle hues, and celestial beauty unlike any other. Chapter 7: Saturn. Saturn is the sixth planet from the Sun and the second largest in our solar system, surpassed only by Jupiter. It is perhaps the most visually striking of all the planets, known universally for its broad, luminous ring system. Saturn orbits at an average distance of approximately 1.4 billion kilometers from the Sun and takes about 29.5 Earth years to complete one orbit. With a diameter of roughly 120,500 kilometers, Saturn is composed primarily of hydrogen and helium. Despite its size, it is remarkably light. It is the only planet in the solar system less dense than water. If there were a body of water large enough, Saturn would float. From afar, Saturn presents a soft, golden hue, with subtle bands of color stretched across its atmosphere. These bands are caused by high-speed winds that circle the planet, reaching velocities of up to 1,800 kilometers per hour. The planet's upper cloud layers are mostly composed of ammonia ice, giving it its pale, creamy appearance. The most iconic feature of Saturn is its ring system. These rings span over 280,000 kilometers in diameter but are only about 10 meters thick in most places, astonishingly thin for such a vast structure. The rings are made primarily of countless particles of ice and rock, ranging in size from microscopic dust grains to boulders several meters across. These particles reflect sunlight, creating the brilliant spectacle visible through even small telescopes on Earth. The rings are divided into several main components. The A, B, and C rings are the most prominent, separated by gaps such as the Cassini division, a dark, broad space between the A and B rings. Numerous fainter rings and ringlets extend beyond, including the Diffusii ring, which is replenished by geysers from Saturn's moon Enceladus. Beneath the rings lies Saturn's dynamic atmosphere. Storm systems, some lasting for months or even years, occasionally appear. The planet's north pole is home to a fascinating atmospheric phenomenon, the hexagonal jet stream. This hexagon, first observed by the Voyager missions and later by the Cassini spacecraft, is a massive six-sided pattern of winds, each side roughly 13,800 kilometers long. The exact cause of the hexagon remains a subject of study, but it likely involves standing waves in the atmosphere. Saturn has over 140 known moons, each contributing to the complexity and beauty of its system. The largest, Titan, is more massive than the planet Mercury and has a dense atmosphere composed primarily of nitrogen. Titan's surface features lakes and rivers, not of water, but of liquid methane and ethane. Beneath its icy crust, scientists believe. Another notable moon is Enceladus. Despite its small size, Enceladus has become a focal point for astrobiological interest. It emits towering plumes of water vapor, ice, and organic compounds from fissures near its south pole. These geysers feed the E-ring and suggest the presence of a global subsurface ocean in contact with rock, raising the possibility of life. Other moons such as Mimas, with its enormous crater resembling the Death Star, and Iapetus, with its stark contrast between a dark hemisphere and a bright one, add to the intrigue. Each moon tells a different story, offering insight into the formation and evolution of Saturn's extended family. Saturn's magnetic field, while less intense than Jupiter's, still stretches millions of kilometers into space. It is aligned closely with the planet's axis of rotation and helps trap particles that form radiation belts around the planet. This magnetosphere interacts with the solar wind, generating faint auroras near the poles. Saturn's rapid rotation, about 10.7 hours per full spin, causes the planet to bulge noticeably at the equator. This oblate shape, combined with the ring system, gives Saturn a distinct and elegant silhouette, even through small amateur telescopes. Our understanding of Saturn was transformed by the Cassini-Huygens mission, which orbited the planet from 2004 to 2017. Cassini delivered detailed images of the rings, explored the atmosphere, and made close flybys of many moons. It even deployed the Huygens probe, which descended through Titan's atmosphere and landed on its surface, the first landing ever accomplished in the outer solar system. Cassini's final maneuver, known as the Grand Finale, involved diving between Saturn and its innermost ring, a daring series of orbits that revealed new information about the planet's mass distribution, gravity, and inner structure before the spacecraft was intentionally plunged into the planet's atmosphere. Visually, Saturn is a world of elegance and wonder. Its softly banded atmosphere, encircled by glowing rings, creates an image of serene majesty. Observing Saturn through a telescope evokes awe, as its ring shape comes into view like a jewel suspended in space. Saturn stands as a symbol of the diversity and grandeur of the outer solar system. Its moons, rings, and atmosphere all combine to make it one of the most studied and beloved planets in the night sky. As our journey continues, we travel even farther from the Sun to a planet tipped on its side, cloaked in methane blue clouds and encircled by faint rings, Uranus. Chapter 8: Uranus. Uranus, the seventh planet from the Sun, is a distant and enigmatic world. It orbits at an average distance of about 2.9 billion kilometers and takes 84 Earth years to complete one orbit. With a diameter of approximately 50,724 kilometers, it is the third largest planet in the solar system and the first to be discovered with a telescope, spotted by astronomer William Herschel in 1781. Uranus is often recognized for its unique tilt. Unlike any other planet, Uranus rotates on its side, with an axial tilt of about 98 degrees. This extreme tilt causes its poles to experience 42 years of continuous sunlight followed by 42 years of darkness. This orientation is believed to be the result of a colossal collision with an Earth-sized object long ago. The planet's atmosphere is primarily composed of hydrogen and helium, with a higher proportion of methane than Jupiter or Saturn. Methane absorbs red light and reflects blue and green wavelengths, giving Uranus its distinctive pale cyan hue. The atmosphere is layered with haze, clouds, and occasionally observed storms, though it appears relatively featureless in visible light compared to the more dramatic atmospheres of Jupiter and Saturn. Beneath the atmosphere lies a thick mantle of icy materials, water, ammonia, and methane, forming a supercritical fluid. Deeper still may be a rocky core. This internal composition places Uranus among the ice giants, along with Neptune. Unlike gas giants, ice giants have a larger proportion of elements heavier than hydrogen and helium. Uranus has a faint and narrow ring system. The rings were discovered in 1977 when astronomers observed them blocking the light of a background star. There are 13 known rings, made primarily of dark, radiation-processed particles. Though not as visually prominent as Saturn's, the rings of Uranus are still a striking and complex feature. The planet also hosts a diverse family of 27 known moons, named after characters from the works of William Shakespeare and Alexander Pope. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, present a variety of surfaces shaped by past geologic activity. Miranda, the smallest of the 5, displays one of the most extreme and varied terrains in the solar system, with towering cliffs, deep canyons, and broken surfaces, evidence of a tumultuous past. Ariel and Titania have canyons and rift valleys carved by ancient tectonic forces. Umbriel is dark and heavily cratered. Oberon, the outermost of the major moons, is also covered in ancient craters and icy scars. These moons, though distant and cold, hint at a complex history of internal heating and resurfacing. One of the most mysterious aspects of Uranus is its magnetic field. Unlike Earth's, which is nearly aligned with its rotational axis, Uranus' magnetic field is tilted at about 59 degrees and offset from the planet's center. This leads to a highly asymmetrical and dynamic magnetosphere that changes orientation dramatically as the planet rotates. Uranus rotates once every 17 hours and 14 minutes. Despite its slow orbit, its day is relatively short. The planet's rotation and tilted axis result in unique seasonal effects. At solstices, one hemisphere faces the sun almost directly, while the other lies in extended shadow. During equinoxes, the Sun rises and sets around the equator like on Earth. These shifting conditions contribute to subtle but evolving atmospheric changes. Our most detailed observations of Uranus come from the Voyager 2 spacecraft, which flew by the planet in 1986. It revealed Uranus as a calm, bluish world, measured its magnetic field, and imaged its moons and rings. Since then, telescopes like Hubble and ground-based observatories have tracked changes in its atmosphere, including occasional bright spots, evidence of large storm systems forming far beneath the clouds. Uranus remains largely unexplored compared to the inner planets and even Jupiter and Saturn. Future missions, such as orbiters or atmospheric probes, could help unlock its many mysteries, its tilted magnetosphere, its internal structure, its peculiar ring system, and its icy moons that might hold secrets of their own. Visually, Uranus offers a quiet and distant beauty. Its soft blue glow, faint rings, and sideways spin make it one of the most unusual members of the Solar System's planetary family. Observing Uranus requires patience and powerful instruments, but the rewards are a glimpse into a world shaped by forces and histories very different from those of its neighbors. As we leave Uranus behind, our journey carries us to the final known planet of the Solar System, a deep blue giant cloaked in supersonic winds and shadowed storms, Neptune. Chapter 9: Neptune. Neptune, the eighth and most distant planet from the Sun, is a majestic world cloaked in deep blue hues and shaped by the strongest winds in the Solar System. It orbits the Sun at an average distance of 4.5 billion kilometers and takes nearly 165 Earth years to complete one orbit. Discovered in 1846, Neptune was the first planet found through mathematical prediction rather than direct observation. With a diameter of approximately 49,244 kilometers, Neptune is slightly smaller than Uranus but more massive, making it the densest of the four gas and ice giants. It is classified as an ice giant due to its interior composition of heavier elements, including water, ammonia, and methane ices, surrounding a rocky core. The planet's striking azure color comes from the absorption of red light by methane in its upper atmosphere, combined with other yet unknown components that deepen the intensity of its color. Though visually similar to Uranus, Neptune's atmosphere is more active and dynamic. It features massive storm systems, rapid winds, and high-altitude clouds made of methane ice crystals. One of the most prominent features ever observed on Neptune was the Great Dark Spot, a massive storm system comparable to Jupiter's Great Red Spot. First imaged by Voyager 2 in 1989, the storm was large enough to span the Atlantic Ocean. Unlike Jupiter's long-lived vortex, however, Neptune's dark spots appear and vanish over time, revealing a highly transient and turbulent atmosphere. Neptune's winds can reach speeds of over 2,000 kilometers per hour, the fastest recorded in the Solar System. These winds drive bands of clouds that form white, wispy streaks across the planet's atmosphere. High-altitude clouds made of frozen methane appear to cast shadows on the deeper cloud layers, offering depth and contrast to the planet's shimmering surface. The atmosphere is layered, with an upper region dominated by hydrogen, helium, and methane. Beneath lies a mantle of slushy, superheated water, ammonia, and methane in a fluid-like state. At the center is a solid core composed of rock and metal. Despite its great distance from the Sun, Neptune emits more than twice as much energy as it receives, suggesting an internal heat source, possibly residual heat from its formation or slow gravitational contraction. Neptune has a faint, dusty ring system composed of 5 principal rings and several fainter arcs. The rings are dark and narrow, likely composed of radiation-darkened material. They are named after astronomers who contributed to Neptune's discovery and study: Gall, Leverrier, Larsell, Arago, and Adams. Some of these rings feature bright clumps or arcs, possibly maintained by the gravitational influence of nearby moons. Neptune has 14 known moons. The largest and most intriguing is Triton, a world unlike any other. Triton is the only large moon in the solar system that orbits its planet in a retrograde direction, meaning it moves opposite to Neptune's rotation. This unusual orbit suggests Triton was once a Kuiper belt object captured by Neptune's gravity. Triton is geologically active, with a surface shaped by cryovolcanism and geysers that spew nitrogen gas into space. It is one of the coldest objects in the solar system, with surface temperatures near -235 degrees Celsius. Its icy terrain includes smooth plains, ridged landscapes, and mysterious cantaloupe terrain marked by knobby ridges. Triton's tenuous atmosphere and evidence of subsurface activity make it a compelling target for future exploration. Voyager 2 remains the only spacecraft to have visited Neptune, flying by in 1989. It provided invaluable data and images, revealing the planet's storms, rings, and moon system. Since then, Earth-based telescopes and the Hubble Space Telescope have tracked changes in Neptune's atmosphere, including the appearance and disappearance of dark spots. Neptune rotates once every 16 hours and has an axial tilt of about 28.3 degrees, resulting in seasonal changes during its long orbit. Each season lasts over 40 Earth years. The planet's magnetic field, like that of Uranus, is tilted relative to its rotation and offset from its center, creating a complex and shifting magnetosphere. Despite its remoteness, Neptune has a profound influence on the structure of the solar system. Its gravitational presence helped shape the Kuiper belt, a vast region of icy bodies beyond its orbit, and continues to interact with comets and other trans-Neptunian objects. Neptune stands as a sentinel at the edge of the known solar system. Its vivid coloration, fierce weather, and unusual moons highlight the diversity of planetary environments. As we conclude our journey through the solar system's primary planets, Neptune reminds us that even the most distant worlds are rich with mystery, waiting for the day when humanity returns to explore them up close. Beyond Neptune lies the Kuiper belt and the vast expanse of interstellar space, a frontier ripe for future discovery. Chapter 10: Beyond the Planets. As we leave Neptune behind and gaze even farther into the depths of space, we cross the boundary into the Kuiper belt, a sprawling region filled with icy remnants from the solar system's formation. Here lie dwarf planets like Pluto, Haumea, Makemake, and Eris, along with countless icy bodies and comets. These distant objects follow elongated orbits, whispering tales of a time when the solar system was still young and chaotic. The Kuiper belt marks the edge of the planetary realm, but the journey does not end here. Farther still lies the hypothesized Oort cloud, a vast spherical shell of icy bodies extending nearly a quarter of the way to the nearest star. It is from this region that long-period comets occasionally make their way into the inner solar system, streaking across our skies like time travelers from the ancient past. As our understanding grows, so too does our awareness of how vast, diverse, and dynamic our solar system truly is. The Sun, ever shining at the center, binds each of these worlds in its gravitational embrace, from the scorched surface of Mercury to the frozen twilight of Neptune and beyond. Every planet, moon, ring, and asteroid holds a piece of the story, a narrative etched in rock and ice, gas and light. Missions past and future continue to unveil new chapters, sending back data, images, and discoveries that transform our perception of the cosmos. We are fortunate to live in a time when humanity is not only observing the heavens but reaching out to them. Rovers traverse alien planes. Telescopes peer into distant galaxies. Probes cross the boundaries of known space. The solar system, once an abstraction in the sky, has become a tangible neighborhood, familiar, yet still brimming with wonder. And so, our journey through the solar system comes to a close. Yet this ending is merely a beginning. The more we explore, the more we realize how much there is left to discover. In the quiet orbits of distant planets, in the icy heart of a passing comet, or in the sunlight filtering through Saturn's rings, the universe calls us forward, gently, persistently, endlessly. Thank you for joining us on our journey through the solar system.